Hey, okay, so this video is going to be a little bit different today because what this video is going to do is I'm going to show you how to read scientific texts. Okay, now it's really important to know how to do this because a lot of times, especially if you plan on going to college, it's important to know how to read a text and take good notes from that text because sometimes you'll have professors that you don't really understand or they don't explain the information very well. So then it's your responsibility to then go and find other resources. And some of the time, those resources are textbooks. Okay. And reading science is not entirely different than reading just normal literature or nonfiction literature, but it is sometimes can be a little overwhelming because scientific texts tend to be very wordy with vocabulary, right? So it's important to know that when you're reading something, you're reading with a purpose instead of just sort of like going over the words, okay? And so that's why I'm going to show you how to take notes as you read a text, okay? So what we're going to use is this thing. It kind of looks like this. It's called combination notes. We're going to do an informal outline of a section. And then I always like to draw pictures because I am a visual person. So if I can draw a picture of something to help me remember that vocabulary word, it really helps me remember the information. Okay, so this is actually a new unit that we're starting, and it's called thermochemistry. But before we start that, we have to talk about the nature of energy. So that's what this section is. Okay. Now, there's different things. Texts are set up different ways. Okay. I always like to read the intro paragraph to the section just so I can sort of get like a broad understanding of what I'm going to be looking at. Okay. So since I'm reading section 5.1 first, that's what I'm going to read. Okay. So it says the nature of energy. So it says we begin by considering the nature of energy and the forms it takes, which is telling me that I can have multiple forms of energy. Notable kinetic energy, I've heard of that before, and potential energy, I've also heard of that. Okay, so they're italicized, so that tells me that they're probably going to be important words within this section. Then goes on to say, we will also discuss the units used in measuring energy. Okay, so energy is something that we can measure. Okay, so if we can measure something, chances are we're going to have a unit for it. And the fact that energy can be used to accomplish work or to transfer heat. Okay, so now here are two different forms of energy that I know that I'm going to be reading about. I'm going to be reading about work energy and I'm going to be reading about heat energy. Okay, to study energy changes, we focus on a particular part of the universe, which we call the system, and then everything else is the surroundings. Okay, so here are two new vocab words that I'm going to have to look for when I'm reading this section. Okay, so now that I read that, I'm going to go to the start of the section, which is the nature of energy, and I'm just going to start reading. Okay, and it says, although the idea of energy is a familiar one, which I mean, you've looked at energy in one way or another throughout your course of schooling. I at least hope so. And it says, but it is a challenging to deal with in the concept in a precise way. Energy is commonly defined as the capacity to do work or transfer heat. Okay, here's a definition. So that is going to be important for me to note this definition of energy. Okay, and it specifically says that energy is the capacity. And if you don't like the word capacity, you can change it. Okay, capacity is fine for me. You can change it to ability, any synonym that makes more sense to you than capacity. If you want to change it, change it. These are your notes, okay? So it's the capacity to do work or transfer heat, okay? So energy, you may be familiar with the work one, right? Because that's the most common one. Well, in chemistry, we talk a lot about heat because we can't really see our particles do work because they're so small, okay? Okay, so then it goes on. It says the definition requires us to understand the concepts of work and heat. Okay, so it's going to go into more in-depth information about work and heat. So then it tells me about work. It says work is the energy used to cause an object with mass to move against a force. Okay, so it tells me specifically what work is. So work is equal to energy used to move an object that has mass. Okay, and then it goes on to say heat is the energy used to cause an object's temperature to increase, okay? So you'll notice that temperature is in the definition. So heat and temperature are not the same thing. You can't use the word inside of its own definition. So that's important to note. So heat is the energy required to cause temperature increase. Now you'll notice that I changed the definition a little bit because I like to think about heat as, okay, well, something's temperature is changing. That's how we can tell if something's heating up or not, okay? All right, so I'm going to keep going now. And it says, we will consider each of these concepts more closely. Okay, now I come to my first big, bold thing here, right? Okay, it says kinetic and potential energy. So that's going to be my first thing that I'm reading about. Okay, so I'm just going to write it in terms of kinetic and potential energy, and I'm going to give it a number 1, okay? And then I'm going to have like bullet points underneath it as I'm reading along based off of the information that it wants me to, or that I think is important, okay? Because that's what I'm doing when I'm taking it. Okay, it says objects, whether they are a tennis ball or molecules, can possess kinetic energy, the energy of motion. Okay, so kinetic energy is my motion energy. All right, and then it keeps going. It says the magnitude of the kinetic energy of an object depends on its mass and its volume or velocity. Or it says speed, but v is velocity because velocity deals with direction as well. So it says kinetic energy is equal to 1/2 mass times velocity squared. So that's the equation for that. It says equation 5.1 shows the kinetic, I'm sorry, this is not straight. You guys are probably getting mad at me because I don't have it straight. Let me move it to where it is straight. Uh-oh, I lost it. Okay, so then it goes on to say that the equation shows that kinetic energy increases as the speed of an object increases. So if you look at the equation that it gives me, they're on kinetic energy and velocity and mass are on the opposite sides of the equation, which means they're directly related to each other. So if mass increases, kinetic energy increases. If velocity increases or speed increases, kinetic energy also increases. Okay, so I don't really need to write that because I can look at the equation and know. Okay, for a given speed, the kinetic energy increases with increasing mass. Thus, a large sport utility vehicle, blah, 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 blah. Okay, now, I'm saying blah, blah, blah because I already know, I've already seen the mathematical equation, so I don't really need to think about what that's saying because I know that they're directly related to each other. This is important, though. It says, atoms and molecules have mass and are in motion. Therefore, they possess kinetic energy. Okay, that's important. Okay, all other kinds of energy, the energy stored in chemical bonds, is the potential energy. So it says an object can possess potential energy by virtue of its position relation to other objects. So potential energy is my not moving energy. Okay, so kinetic's moving, potential is not moving. That's what it says. Okay. Potential energy arises when a force operates on an object. A force is any kind of push or pull. So here we go. Here's a definition. So force is equal to a push or pull on an object. I'm going to keep it short and sweet here, okay? The most familiar is a pull of gravity. Okay, so now I have the definition of kinetic and potential energy. So I'm going to draw a picture now, okay, to illustrate this for myself. Okay, so if I have a hill, and this is kind of what the image is showing a little bit in the text, and I have a ball, okay, if that ball sits on top of the hill, it just has potential energy, right, because it's sitting. If the ball starts to move down the hill, okay, what's happening to the potential energy? Well, potential energy is going to go down because it's moving away, it's actually moving, so the potential energy is turning into kinetic energy, and the kinetic energy is going up, okay? And that's sort of what the image is showing by virtue of this bicycle. Okay, so let's keep reading here then. Okay, now it gives me the equation for potential energy. So the potential energy is equal to, and I'm going to write that, so potential energy is equal to mass times gravity times height. So potential energy is directly related to the object's mass. the gravity on that object, and how high that object is up, okay? Keep reading. The height of the bicycle is relative. G is the gravitational constant. Once in motion without any further effort or on her part, the cyclist gains speed as the bicycle rolls down the hill. Her potential energy decreases as she moves downward, but the energy does not simply disappear. It is converted to other forms of energy, principally kinetic energy, the energy of motion. Okay, so that's what we drew our image of. Okay, now gravity is an important force for large objects, but in chemistry, we don't really deal with that because our objects are very, very tiny. Okay, so we're going to keep reading here. It says small objects, gravitational forces play a very small role in the ways these submicroscopic objects interact with each other. Forces that arise from electrical charges are more important when dealing with atoms and molecules. One of the most important forms of potential energy in chemistry is electrostatic potential energy, which arises from the interactions between charged particles. The electrostatic potential energy. So electrostatic seems like a pretty, big word, okay? I want you to think about it in terms of what you know about electrostatic. You know that if you rub your feet across the ground, you're generating an electrostatic current because then you touch a doorknob, you're going to get shocked, okay? So basically, it's the buildup of electrons in an atom, okay? Which is proportional to the electrical charges. Okay, so then it gives me an equation. So here now I have the energy of electrostatic, and it tells me it's equal to K, Q1 times Q2 divided by D. And then I'm assuming it's going to tell me what each one of these things means. So I'm going to keep reading. It says K is simply a constant. So it tells me K is a constant. It doesn't change. Okay. Q1 and Q2 are the magnitude of the charge of the electron. Okay. When Q1 and Q2 have the same size, they're both positive, they will repel each other. Or if they have opposite, they'll attract each other, okay? So one of our goals is to relate the energy changes that we see like at a microscopic. So like if I actually see something, I see a temperature change, how do we relate that to how atoms move, okay? All right, so that's basically the big stuff in that first section. Then I'll notice that it says units of energy. So that's going to be my second thing. Or actually, you know what? I'm just going to make it its own little thing because it's talking about is the unit, okay? So basically, this is where it's showing me how I eventually get to this thing called a joule, okay? So in chemistry, we say that energy unit is joules, okay? And that's really important. All right, so I'm going to keep reading. I come to a big topic here, system and surroundings. So I'm going to go to my notes and I'm going to write system and surroundings. Now you'll notice I'm not writing everything down. I don't like to write a lot, okay? I just write what I think is important. Okay, so it says and I can always go back if I'm answering a problem and I don't have that information in my notes, I can always go back and reread. It's not the end of the world, okay? So when we analyze energy changes, we need to focus our attention on limited and well-defined part of the universe to keep track of the energy changes. The portion we single out for study is called the system. Okay, so the system is what you're looking at. The system is what you're studying. Okay, then which probably means the surroundings is everything else. So let's keep reading. System, everything else is called the surroundings. Exactly. So that's what it says. So the surroundings, everything else. Okay. Now, I am going to stop here because I'm running out of time on my video. What I'm going to do is you are now going to finish this section, taking your notes, and then I'll look over them to make sure that you can move on to the next section. Okay, I hope this was helpful. We'll walk through this a little bit more in class, and if you need help, just let me know. Thanks.